Yeah, so it's a pleasure. It's a pleasure to invite Chandan Saha from the Indian Institute of Science. So he'll be giving two talks on reconstruction, arithmetic circuit reconstruction. So this is the first of his talks. The next talk will be on Friday. Yeah, Chandan, the floor is yours.
Yeah, thanks, Giri. Thanks for introducing me. I would like to begin by thanking the organizers for the invite to give a talk. So it would be an introductory talk on arithmetic circuit reconstructions. I have split the content into two parts, part 1 and part 2. I intend to cover the first part today and the next part on Friday. So in the first part, I'm going to talk about worst case reconstruction, and in part 2, we're going to talk about average case reconstruction. Right. So, but before I start, I should apologize. Like the slides are a bit hastily made, so sometimes they're a bit clumsy, and not all the details are there. So please feel free to stop me and interrupt anytime. Right. Okay. So without further ado, let me start. Because for some reason my slides don't move. Yes, it moves now. Okay. So you've seen this picture or similar picture several times, I guess, in this series of talks. So an arithmetic circuit computes polynomials in a very natural way. There are addition and multiplication gates, and the inputs are variables, and the output is a polynomial. Right. So, and the size of such a circuit is the number of gates and wires in it, and the depth of the circuit is the length of the longest path from an input to an output node. Okay, so what's the reconstruction problem? It's the learning problem. It's a learning problem for arithmetic circuits, right? So formally, suppose your f is an n-variate polynomial of degree d, right? That is computed by a circuit of size S from a class C. Right? So C is a class of circuits. Right? For example, the 3 circuits or the 2 circuits and so on. And the reconstruction problem for this class C is the following. You're given black box access to this polynomial f, and you want to output a small circuit computing f. Right? So what does black box access mean? It means that you're only allowed membership query access. That means you can pick your favorite point, right? And you want the evaluation of the function at that point. Yeah, that is what the black box will return. All right. So how
Lost you, I think.
You got muted, Chandan.
small
Got muted.
Right? So I said it already exists. Sorry? Oh, I got muted.
You were muted. As soon as you started showing the reconstruction problem for C, you got muted, I think.
Okay, can you hear me now?
Yep. Yeah.
Okay, I think, okay. So, yeah, so is this part clear? Okay,
No,
yeah, so I was just saying what black box access means. And now by a small circuit, I ideally want an output circuit that has size polynomial in S. So we are given the assurance that there already exists a circuit of size S, and we want an output circuit which is not much larger than this circuit S of size S, right? And also, ideally, I want an output circuit from the class C. If I'm able to do that, then that kind of learning or reconstruction would be called proper learning for the class C, right? So if the output circuit additionally belongs to the class. But as far as the problem statement goes, we are free to output any circuit, any small circuit for it. Need not be from the class C. Okay, so what about the efficiency of this reconstruction process? Again, ideally, I want it to be a polytime algorithm. Polynomial in what? The parameters, the usual parameters, the number of variables, the degree, and the size, right? Yeah, so I haven't put in the number of variables here because S already subsumes n, right? The size of the circuit. Notice one thing, and this is one simple point, but this is still something to remember, is as far as reconstruction goes, even reconstruction from a verbosely given f is non-trivial. What do I mean by verbosely given f? Let's say f is given to you not as a black box, but as a list of coefficients, right? All its coefficients. How large is it? You have, it's an invariant polynomial in degree d, so you have roughly these many coefficients, right? So you're given this entire coefficient vector, and then you are asked, like, can you give me a small circuit for f? Right? I give you the assurance that there does exist a small circuit. Can you output such a circuit? Even this is non-trivial, because I think of an S which it's neither too small, not too large, right? Too large meaning like it is not as large as the number of coefficients, but it is not too small either. Let's say n cube, right, or n to the 4 or something, right? So, and now if you wish to output a circuit of size S, a naive way would be to search all possible circuits of size S. And if it's an exhaustive search, and if your underlying field is a finite field, let's say, then you can definitely carry out your search. But that search would take time exponentially, right? So, if S is like n cube, then this trivial process gives you running time 2 to the n cube. Whereas the number of the input size, which is again linear in n, right? So it's still not polynomial in the input size, which is like n to the d, right? So it's something to keep in mind, that it remains a non-trivial problem even if f is given verbosely. So we are making our life harder by giving input a black box access to f. Right. So by definition, reconstruction is an exact learning process. What do I mean by this? I mean that the output circuit must compute f exactly, right? We have no choice, actually. We have no choice, because if we insist on outputting an arithmetic circuit, then we must be computing f, right? Because if you compute any other polynomial, two distinct polynomials would be differing at too many points, right? So they're far from each other, right? There are not too many common roots, right? So that's why, unlike learning Boolean functions, where you can perhaps output another Boolean function which differs from a few points, differs at a few points, you can't do that with arithmetic circuits. You have to output the function exactly if you insist on outputting an arithmetic circuit. But people have studied pack learning in the context of arithmetic circuits. What does that mean? It means that now, instead of looking at the entire function, I can think of learning the function over a certain domain, right? So, for example, you can think of learning Boolean functions that match the output of arithmetic circuits on the Boolean hypercube, right? So in that case, like, you're free to output an arithmetic circuit. It's just that I'm not interested in the overall polynomial. I'm only interested in the evaluation of the polynomial on the Boolean hypercube, and checking how far my output Boolean function differs from the original function. Right? So in that case, pack learning or approximate learning would make sense, right? Sort of exact learning, and people have studied that and showed some hardness result. Talking about hardness, like, let's say it's an obvious question now. Like, by now we have, in this series of talks, we have seen arithmetic circuit lower bounds, and we've seen polynomial identity testing, right? And here is a third problem: learning arithmetic circuits. And so, how hard is this problem, right, compared to the other problems? It turns out that it is at least as hard as proving lower bounds. Yeah, that's because of a neat result by Portnoy and Flygons. It says that any randomized polytime reconstruction algorithm for a class C implies a super polynomial lower bound for the same class C. Right? That's, the statement is reasonably neat. So naturally, it is as hard as proving lower bounds for C, and people have focused on learning circuit classes for which non-trivial lower bounds are known, right? So and it's now an obvious question: is the complexity of learning the same as proving lower bounds, or can I expect an affirmative answer to the question that does lower bound imply learning or reconstruction? Right? Unfortunately, I think that there are plenty of evidences that suggest that reconstruction is an inherently hard problem. Right? For lower bounds, we might still believe that we might be able to prove super polynomial circuit lower bounds. Right? One might be optimistic about this. But as far as learning goes, it seems that it is an inherently hard problem, irrespective of whether or not we're able to prove lower bounds. Right? So I say evidences, not much concrete results on this. So what I'll do is I'll try to draw analogy with what is known, what kind of hardness is known in the Boolean world, and just for the sake of drawing an analogy, let me define this very well-studied problem, a very popular problem called the minimum circuit size problem. Once again, in this statement, I'm talking about just the Boolean circuit complexity, right? Not arithmetic circuit, but it's a small digression. I'll come back. So the problem statement is the following: you're given a truth table T, right, of size 2 power n, so it's the function has n variables, and an integer s. And you wish to check if there exists a function defined by this truth table, right? If the function defined by the truth table has a circuit of size at most s, right? So it's no one is quite sure what's the exact hardness of the problem. Some people believe that it has intermediate complexity. Some people believe it is NP complete, right? But the status is one of a long-standing open problem in complexity theory, and it's still being very actively researched upon. Right, but I'll state one result which is quite relevant for our purpose, and that's the problem of approximately learning the minimum circuit size. If you think for a while, you'll realize that the reconstruction process, the learning process, automatically is trying to output a small circuit. Right? So if your smallest circuit has size s, you're trying to output a circuit which is of size poly s. So you're naturally trying to approximate the minimum circuit size, right? And that's inherent in the process, right? So, and what this result by Allender and Hirahara says about Boolean complexity is that approximating the minimum circuit size, of a Boolean function to within very close to n is the size of the truth table, right? N to the 1 minus log of 1 factor is not in P, assuming existence of one-way functions. But a factor n approximation is easy, right? Because n is the size of the truth table. You just output that, the whole truth table, the DNF that's corresponding to it, and you're done. Right? But anything slightly non-trivial becomes difficult, right? So, and one might expect that something similar holds even for arithmetic circuit complexity. So let me define an arithmetic MCSP version in a very natural way, that you are given the coefficient vector t, right? Instead of a truth table, you're given the coefficient vector t of size whatever, and it's an n-varied polynomial of dpt, and you're given an integer s, and you want to check if the polynomial defined by this coefficient vector has an arithmetic circuit of size at most s1, right? And by drawing analogy with the Boolean work, it's not too far-fetched to conjecture. Let's say that a similar thing, like n to the 1 minus log of 1 approximate MCSP for arithmetic circuits cannot be done in polynomial time under certain, let's say, widely believed assumptions like one-way function. I don't have a clear idea yet as to what kind of assumption sounds good here in this context. So as I said, like no one knows whether this is true or not. It's an open problem, but it seems plausible thing now that we know a similar result for Boolean circuits. All right. So what this means is, like, one cannot hope to learn general circuits too efficiently, right? It seems like an inherently hard problem, and we do know of concrete hardness results for special or restricted classes, of arithmetic circuits. Right. So, sorry, am I still connected or got dropped off? I suppose.
No, we can hear you. Yeah,
we can hear you. Yeah.
Oh, now we lost
can
the
you
share
speak?
screen.
Oh yeah. Oh,
Yeah. Okay. Let me try to
Is
share
one
my
of you,
screen.
both of you are there, but one of you has not is no longer. It's fine.
Yes, the screen is visible now.
Yeah.
Okay.
Yeah.
Thank you. Yeah. Right. So, I'm muted now. Okay.
Oh, Chandan,
No,
okay.
it's fine.
Okay. Right. So no, I'm getting all kind of messages on my screen, like you're muted, you're this, that. So, okay. Okay. So, right. So, for example, for the class of set multilinear depth-3 circuits, we do know of a hardness result. It's a very classical result shown by Hostad. And not only that, we know that constant factor approximation of the minimum sized set multilinear depth-3 circuit, which is basically the tensor rank, is NP hard, right? But still a small constant, it's like 1.0005 something, right? And we know of a similar hardness result, not the approximate version, but the actual version, like finding the minimum size circuit, also for another restricted class of circuits called depth-3 powering circuits. Right? I'll come to this circuit in particular because both for part 1 and part 2, depth-3 powering circuit is at the center stage of both the talks. So I'll formally define and say what all things are known and not known. So, for example, this is not known. Whether constant factor approximation of finding the minimum size depth-3 powering circuit is hard or not, right? In other words, whether approximating the powering rank to a constant factor, maybe a very small delta like 0.0005, whether that is NP hard or not is not known. It's kind of a bit strange and annoying, like that it is known for tensor rank, but not quite the powering rank or the symmetric tensor rank. As far as I know, I may be mistaken, but as far as I know, it is not known. But still, despite all these negative results, people have studied the learning problem or the reconstruction problem for various natural classes of arithmetic circuits, subclasses of arithmetic circuits, right? And basically for two reasons, because these models are, although restricted, they're itself quite themselves quite interesting, and besides, like there's always the hope that by studying restricted version, you might get more insight and might end up discovering more interesting proof techniques and strategies, right? So yeah, so these are the two main reasons. And as I say, like problems like the tensor rank and Waring rank, they themselves are fundamental problems. So it's definitely worth studying the complexity of finding them or approximating them. All right, so here is a list of some of the models that important models that people have studied, which can be broadly classified into two types: constant depth arithmetic circuits and constant read arithmetic circuits. Right? I won't be covering all of them. I would be stating what is known for these models, but I'll try to cover in some details at least these three. I'm sure some of you already know, but this talk is an introductory talk and primarily meant for students. So let me go into the details.
We lost him. We lost your voice. You're muted again, I think. Chandan, you're muted.
Much of the time would be spent on CSL. Again, I'm muted.
Yeah, now.
How about now?
Yeah, now it's okay. Yeah.
Okay. Okay. Right. So I was just saying, like, all these algorithms are worst case learning algorithms. So let me go into it. But before I begin, I should definitely mention one result which almost always gets used in these reconstruction algorithms, and that's the famous polynomial factoring algorithm, right, by Kaltofen and Trager. Right. So what this means in our context is the following assumption or a convention, that we'll always assume that the top gate of the circuit is a plus gate. Why not a multiplication gate? Because if it is a multiplication gate, then it factorizes, right? It's 2 factors, and each of these factors are simpler circuits, let's say of smaller depth, right? So, and this is where this black box polynomial factoring algorithm by Kaltofen and Traeger comes in handy. It states the following: that given black box access to an n-variate degree D polynomial f, we can compute black box access to all the irreducible factors of f in randomized polytime. Right? There are some minor restrictions on the field size and the characteristic of f. Let us ignore that. Yeah, so that's why, like, if you're given a polynomial whose top gate is a product gate, you can always find all the factors and then try to reconstruct the factors, which are possibly simpler circuits. Right? Okay. So with this, let me start depth 2 reconstruction. Right? It's a very widely studied problem. People are still studying it in certain context. So what's a depth 2 circuit? A depth 2 circuit of size s computes a sum of at most s monomials. Now, such a polynomial is called an sparse polynomial. The corresponding reconstruction problem is obvious, that you're given black box access to an n-variate degree D sparse polynomial f, and you want to find its dense representation. You want to find its coefficients and the monomial. Right? And this problem is also known as the sparse polynomial interpolation problem. So as you can see, people have studied it intensely, right, since a few decades now. And now we know of a deterministic polytime algorithm to do sparse polynomial interpolation. And as I said, people are still studying it in certain contexts. For example, like in the context of, instead of membership query access, suppose you only know evaluations of the polynomial at random samples, right? Can you still do sparse polynomial interpolation? And people are studying, but those algorithms still don't have complexity, which is polynomial in all these parameters and DNS. So I'll present this algorithm by Clivans and Spillman. So let me write down f. F looks like this, right? It's a sum of monomials, right? The exponent vectors are EIs and the coefficients are CIs. So for the sake of concreteness, let's assume that the underlying field is a field of rational numbers. What's the input? The input is black box access to f, and the output I want the coefficients and monomials. At a high level, the algorithm has 2 steps. You first discover the coefficients, and then you discover the exponent vectors, right, or the monomials. So let me go into the steps one by one. So here's a very short and simple algorithm to do the first step, so which will recover these coefficients C1 to Cs. Right? First, we pick a prime, which is larger than some polynomial in NDNF. For concreteness, NDS square. How first can we do this? Well, we can do it in a brute force way. Like, we don't have to employ deterministic primality or anything. We can do it in a very brute force way, because we always know that there are primes between n and 2n, right? So you just go over all of them and do a primality check, and that too in a very brute force manner you do it. And this is fine, because I'm tolerating complexity, which is polynomial in NDNS, right? I'm not worrying about the bit complexity of the prime p. Okay, so you do this first step. You pick a prime, and then you define a bunch of univariate polynomials. They are univariate polynomials in X. How many of them? N, again, poly S, right? It's a ns square, just for the sake of concreteness. How are they defined? Let's for an integer t in this range, yeah, you define it as follows. You, in place of the first variable of f, you plug in x. In place of the second variable of f, you plug in x to the t mod p, right? And in place of the last variable, you plug in x to the t to the n minus 1 mod p. There's a double exponential happening here, right? So what you can do is you can first compute t mod p, t square mod p till t to the n minus 1 mod p separately. And then you can do the substitution and define your univariate polynomial GTX, right? So And this can be done again, efficiently in a very brute force manner. You may not do repeated squaring. Let's say you want to compute t to the n minus 1. You do it in a very brute force manner, t times t, then t times t times t mod p, every time you do mod p. Right? Every time, everything is happening in time polynomial in n dns. Right? So what I know at this point, that if I define gt like this, then the degree of gt as a univariate polynomial in x can be how large? It can be at most p times g, right? Because the degree of f is d. And the substitution, because I'm going mod p, it is making sure that the degree of each of this x in the substitution is at most p. Right? So the overall degree of this univariate polynomial gt can be at most pd. Right? So, and p is polynomial, so you can interpolate gt. You can just evaluate gtx at a bunch of points, and then so you do this for all t from 1 to n squared and pick the one GTX. There can be multiple, but pick any one GTX which has the maximum sparsity, right? So, and you output that t and GTX. That's your step one, right? What do I mean by maximum sparsity? Every time you're getting a univariate polynomial, right? You count how many coefficients are non-zero. That's the sparsity of GTX, and you output the one with the maximum sparsity. Right. So we know that this procedure is efficient, but why does it work? Right. So let's see, why does it work in outputting the coefficient vector? So let's say EI is this coefficient vector, right? E1 0 to E1 n minus 1. I'm denoting the variables by x0 to xn minus 1. So that's the exponent vector, right? And associate a univariate polynomial with this exponent vector. Let's call it capital EI. What is this univariate polynomial? It is defined like this: EI0 plus EI1 y all the way to EI n minus 1 y to the n minus 1. Right? So I'm associating a univariate polynomial with the exponent vector. And maybe you can guess, like, why are we doing this? Because of this substitution. The substitution has this nature, right? So think of any monomial, right, whose exponent vector is EI. How would it look like? If I forget mod p for the timing, it would look essentially like this with y replaced by t. Right? That particular monomial will have degree exactly EIT. Right? So that's why we are defining this univariate polynomial. And let's see why it is interesting. Now, notice one thing: the exponent vectors are different. Right? So if they're different, then these univariate polynomials are also different from each other, right? And especially like in FP, they're different. Why is in FP they're different? Because I have chosen a P which is sufficiently large. In particular, P is larger than both n square as well as d, right? In particular, it is larger than d. Because it is larger than d, it is larger than each of these EIJs, and hence the univariate polynomials mod p are also different, right? So now, how many pairs of such E polynomials are there? EIJs are there, right? If I pick any pair, there are n choose 2, roughly S choose 2, right? Because there are S monomials, so roughly S choose 2 monomials are there. Pairs of univariate polynomials, EIs are there. So S square many, roughly. Now, notice one thing. The claim is that there exists a T in the same range, n squares, such that the evaluation of these univariates, right, polynomial EI at T, right, they differ modulo P for every pair INJ. Why is that? Because for every pair EI, EJ, how many T's can be there where they coincide, right? Each such T would be a root of the univariate polynomial EI minus EJ, right? Which has degree at most n minus 1. So there can be n minus 1, bad T's like roots, where EI and EJ are the same, right? And this can happen for any one pair, and there are S square many pairs. So how many such bad T's can be there, where some EI T is becoming equal to some EJ T mod p. So this subscript here basically means that they're not equal mod p. Right? So that number can be at most n square, right? So because I'm choosing t from a large enough range, I'm sure that there does exist a t such that this condition holds, that ei and ej are not equal modulo p when evaluated at t, and this happens for every pair, right? Which is interesting, which basically ensures that all these monomials are basically going to different buckets. Right? So why is that? Now let us define dit as the same, very much like EIT, but I'm defining it modulo p, right? That it is EI0 plus EI1 t mod p and so on. Right? Now you see that the monomial which had exponent EI will now, as a univariate in X, will now have exponent or degree dit, right? So that's why we define dit. And from the way EI and EI are defined, they are equal modulo p. dit is an integer, right? So they're equal modulo p. Fine. So now, because we know that there exists a t such that EIT and EJT are not equal modulo p, that also means that dit and djt as integers, no longer mod p, as integers, they must be not equal. Because if they are equal, then even they must be equal modulo p. And that will contradict the fact that EIT and EJT are not equal modulo p, right? Because dit and EIT are equal modulo p, right? So this means that this univariate polynomial, right, for this nice choice of t, there exists such a t, such that this univariate polynomial GTX will have sparsity exactly s, right? And not only s, its coefficients would be exactly the coefficients of the original polynomial, because all these dits are becoming distinct for this choice of t. And from the way it is defined, it's also obvious that sparsity of GTX cannot be more than s, right? Because it's just an evaluation of the original f, right? What can happen is that sparsity can become strictly less than s if 2 degrees become equal, right? So and this ends step 1, right? That there will exist a t such that GTX will have maximum sparsity, and if you interpolate, you will get the coefficient vector. Yeah, please stop me if you have questions. Right. So now let's do the second step. The second step is recovering the exponent vector. Right. Assuming that we have this good t and good GTX from step 1. Right. And this step is reasonably easy. What you do is now you define another univariate polynomial. Call it aj, right? Where j runs over 0 to n minus 1. And aj would be very much like GT, except that at the jth position, instead of plugging in x power t to the j mod p, you plug in a 2, an extra 2 factor there. If you do that, just imagine, I've written below, just imagine what happens if you do this. Right? For the same t value, right, which is the good t, right, coming from step 1. My GT looks like this. All the DITs are distinct. How would my HJX look like, right? So it will look like that this, pretty much the same as the coefficient vectors of GTX, except that I'll now have a 2 power EIJ scaling factor, right? And now by comparing the coefficients of AJ and GT, I would be able to discover EIJ. Right, coefficient wise, like, okay, because all the degrees are different, right? So you match the degrees of this monomials, and then you divide the corresponding coefficient of Aj by the coefficient of GT. That will give you 2 power EIJ, and from that you get J, right? Just one component of the exponent vector. Right? I'm discovering EI whole of EI. So if I go over all possible J values from 0 to n minus 1, then I end up discovering the whole of EI, right? So, and and I can do the same thing for all I now, right? For
Chandan, we lost you again. Voice, you're muted again.
for all the S many exponent vectors.
Yeah.
Can you hear me now?
Yeah,
Okay.
now we can. But anyway, it was clear. It was very clear.
Right. So, right. So the purpose of choosing the field to be a rational number is so that I can put a 2 here. If the field is something else, you do something similar. You choose some other element, right? So, and it works. So the point is that whatever element you are choosing, that's known to you. So you can always find EIJ. All right, so this ends the sparse polynomial interpolation algorithm of Cary-Vance and Spillman, which basically works over any field. And if you have any questions, you can ask now on this part.
So what you were saying, there are variants people are looking at. What are the variants that they look at in this?
Oh, so here you see the model is you have membership query access to F, that you can query F at your chosen points, right? And you want to interpolate it. On the other hand, people have studied this variant where you don't have this flexibility. You don't have the power of querying with the point. What you have is you have the evaluations of F at random points. Right? And you would still like to discover F right, from random samples. And yeah, so some of the best complexity known there has still running time exponential in D, and people have studied it over real numbers. And yeah, so it's pretty much an open problem there. How to learn sparse polynomials from random samples. Okay, so we might feel encouraged about but now that we have done depth 2, why not depth 3, right? So can we reconstruct depth 3 circuits? So let me define a depth 3 circuit first. It computes the sum of products of linear polynomials, right? The top gate is a plus, then there's a layer of multiplication gate, and at the bottom you have a layer of plus gates again. And these L's here are linear polynomials of degree 1. The corresponding reconstruction problem is the same. You have black box access to such an F, and you want to output a small circuit, right, for F. How hard is learning depth 3 circuits? There are some indications that suggest that it might be a hard problem, like especially like solving it in polynomial time might be hard, right? So, and that's because of depth reduction results to depth 3, where from a general circuit you squash it and make it a depth 3 circuit, and the size does not blow up. So if you end up learning, or if you learn depth 3 circuits in polynomial time, then that would imply sub-exponential time reconstruction or learning for polynomial size general circuits. Now, I think this is the point where we lack evidence, concrete evidence, but there are indications. By analogy, as I said, there are indications that that this might be a hard problem in general, might not be doable in polynomial time, right? So what do? You feel like stuck even at depth 3. So you ask a simpler question: what if all the linear forms feeding into a product gate, what if they're all the same? Right? This gives rise to a depth 3 powering circuit. Right? So let me anyway formally define it. A depth 3 powering circuit is also denoted as a sigma power sigma circuit, computes a sum of powers of linear polynomials. Right? And this circuit is quite interesting, and it's because of Waddingham. And it's also a complete model, meaning that any polynomial can be computed by a depth 3 powering circuit. Why is that? Because of a result by Fisher, which says that you can compute any monomial as a sum of 2 power n minus 1 powers of linear forms. Right? So since you can compute a monomial, and any polynomial is a sum of monomials, you can also write down any polynomial as sums of powers of linear forms. Right? So the model is reasonably powerful and complete, right? And as I said at the beginning, like people, only look at models for which good lower bounds are known, preferably, exponential lower bounds are known. And it turns out for depth-3 powering circuits, very strong, tight lower bounds are known, right? I'm just stating one of them in the context of Waring rank. So the Waring rank of a polynomial, of a homogeneous polynomial of degree t, which is also called a degree d form, is defined as follows, right? It's the smallest s such that f can be expressed as a sum of s many dth powers of linear forms, right? That's the Waring rank of that. Right? By the completeness of the model, I know this can be done. So what the question is, what's the smallest s? And people have shown that the Waring rank of a monomial, of a general monomial, let's say, the ordering of the exponents are like this: e1 is less than e2 is less than en. That's exactly the products of these quantities, e2 plus 1 to en plus 1, right? So if you plug in all the ei's as 1, then you get basically 2 power n minus 1. So the Fisher's formula that stated here is tight, actually. That's the best you can do, right? So what they're saying that this is the smallest depth-3 powering circuit computing a monomial, right? So, very tight lower bounds, matching upper and lower bounds for even a polynomial. So one naturally becomes very hopeful about it. But recall that there's already a hardness result known now, right? To learn the Waring rank of an f, right? So this was shown by sheet of 16. The proper learning depth-3 powering circuit, which is also known as the symmetric tensor rank decomposition in the machine learning literature, is hard, right? It's NP hard. Right, in the machine learning literature, people basically look at computing or doing this symmetric tensor rank decomposition in the average case, or in a non-degenerate case, which I'm going to come to, in the next part on Friday. So, but the point is, like, we can't. It seems like proper learning, even depth-3 powering circuit, is hard. So okay, so hardness. What do we do? Right. So okay. So here is one way out. What about improper learning? Right. Okay, you don't have to output a depth-3 powering circuit. Give me some other circuit. Right. So when we say give me some other circuit, we need to talk about some alternate circuit representation of depth-3 powering circuits. Right. So that's not immediately obvious. Right. So that a small depth-3 powering circuit also has some other kind of small circuit which might be easy to learn, right? So, and this is where read one's oblivious algebraic branching program come in the picture. They give an alternate representation of depth-3 powering circuit. Why is that? Yeah, that's because of a very simple observation. Let's look at this very simple linear form hi, which is the sum of the first I variables, right? Now you see, by binomial expansion, you can relate hi plus 1 and hi, the bottom line here. You can relate it like this. And if I write this equation as a row vector times a column vector, it would look like this, that I have this row vector 1, hi square all the way to hi to d, and then this, different powers of xi plus 1 along with the binomial coefficients. And that will give me my hi plus 1 to the g, right? Now, what does that mean? That means, like, if I write all the powers of hi plus 1 instead of a column vector, I get a matrix now. Let's call this matrix nxi plus 1. The crucial thing to notice here, nxi plus 1, which is a d plus 1 by d plus 1 matrix, involves only one variable, the xi plus 1 variable, right? And why stop here? Now you can expand 1 hi square hi power d further, right? You will get another matrix which depends on only xi, and to the left of it you will get the vector 1 hi minus 1 square, and so on, right? So what this means is that every power of a linear form, you can write it as a product of matrices. Each matrix involves just one variable. The leftmost matrix has variable x1, the rightmost matrix has variable xn, right? All the intermediate matrices are, let's say, let's say d by d matrices. Like, needn't be. These matrices can be of varying size, right? So, but this is the this is the point. Like, I can express any power of a linear form as a product of univariate matrices, and that too, the ordering of the variables is very precise here. The first matrix has variable x1, next matrix x2, and so on. And this I can do for any linear power of a linear form. And now, you see, since you can do it for any power of a linear form, you can also do it for sums of linear forms, which is the sums of powers of linear forms, which is a depth-free powering circuit. Because you can basically arrange the matrices and make block diagonal matrices, so I should have put in some more details here, maybe drawn a picture, but yeah, please let me know if this is not clear. That the point of doing this is to finally show that any depth-free powering circuit can be computed as a product of univariate matrices, where the first one is a row vector, the last one is a column vector, and things in between are let's say ds by ds matrices involving only just one variable xi. And this representation, products of univariate matrices, that's what an read once oblivious AVP means. Right? So formally, an n-variate read once oblivious AVP, ROAVP, let's say, R is a product of the form m1x1 to mnxn, where mi is some wi minus 1 times wi matrix, depending on just the variable. Sorry, there's a typo here. It should be xi and not xi plus 1. Yeah. And the first one is a column row vector. The last one is a column vector. That's why these widths are 1. And size of such an ROVP is defined as the sum of the widths. And the tuple of this sequence of widths is called the width sequence of R. Right? So that's an ROVP. Okay. So it's interesting because you see, matrix multiplication can be done using a poly-size circuit. So because I have n many matrix multiplication, there is a poly-size circuit corresponding that computes this, the polynomial, which is computed by R. Right? So it is indeed an alternate circuit representation for a depth-free powering circuit. Right, and also this model captures several other interesting models, not just depth-free powering circuits. There are pure formulas, there are non-commutative models, and there are set multilinear AVPs, and ROVP are very closely related to several other interesting models. So it makes sense to study them. Right, so and you can define your reconstruction problem like this. Again, I'm saying output a small circuit, but the whole point of coming to ROVP is to do improper learning. If I again output a circuit which is not an ROVP, it kind of defeats the purpose. But fortunately, we don't have to do that. It turns out that we can do proper learning for ROVP. Given black box access to an ROVP, we can output an ROVP computing the same F. And not only that, we can do something stronger. We can actually output the smallest ROVP computing. Okay, so now I'll go into some details of the ROVP reconstruction algorithm. I'm sure like things are mostly familiar to some of you. Might be a little boring, but yeah, introductory talks, I have no choice. All right, so a little bit of
Can I just ask a question?
Yeah.
So last week,
sure.
Ram Prasad, when he spoke about non-commutative circuits, he showed how to, in some sense, reconstruct the optimal circuit also, right? So is it, and you also mentioned
for ABPs.
ABPs.
ABPs. Yeah.
For ABP.
Oh, did you do that, Ram Prasad? Okay, sorry.
Yeah, I did Nissan's proof. Yeah.
reconstruction of ROVP.
I mean, I did it in the non-commutative setting.
I
That is, I
see.
just
So
showed that non-commutative ABPs can be reconstructed. I didn't show it in the sense of reconstruction, in the sense that the measure exactly tells you what the smallest size is.
Right. Yeah. So the measure tells you the smallest size, and it turns out that you can also reconstruct. So yeah. So I'm sorry. My apologies. It might be a little
I
bit
just
of,
wanted to know. Is it? I mean, no.
Yeah. You're right.
That is not the problem. It is.
Yeah.
So I mean, no. Also, because at that point, I remember Ramprasad mentioning that one should think of non-commutative circuits as really read ones, because you're not using. You mentioned that also, right? I think.
I mean, in the sense that the commutative analog of that is ROABP.
Is ROABP, no? Okay,
Yeah.
okay. Nice to see.
Right. So that's correct. So the underlying ideas, as I'd say, they're the same. Like it comes from Nizan and actually several. For example, this. So let me just briefly say it. Like a randomized algorithm was first given by this bunch of authors in 2000, and I haven't looked at the paper, but I, from whatever I've read from other sources, it seems that they do essentially the things which involve this measure, perhaps which Ramprasad talked about, evaluation dimension, right, and finding the smallest ROVP size, right, and so the underlying ideas would be the same, and I'm pretty sure about that. So let me do it anyway, right? Just for the of it, right? So yeah, because I have some time, like half an hour or so, maybe. Yeah, sorry, I can't hear you.
Sorry, 25 minutes as per my clock. Yeah. You have time.
Okay, sounds good. Okay. So, and there's a deterministic algorithm also known, but that's not polynomial time. It's a quasi-polynomial time algorithm, which is done by basically reducing the learning problem to finding efficient hitting sets for the same model. So let me not go into the deterministic model, but it is closely related to the randomized algorithm. Right. So, okay, so we'll give an overview of the randomized algorithm. Right, so I think things get a little clumsy from this slide, so please bear with me. So let's say this is my ROVP, M1, M2 to Mn, and suppose it's the minimal ROVP, meaning the sum of the width sequence, of the widths in this width sequence is the smallest possible. And you're given black box access to it. You want to output an ROVP, N1, N2 to Nn, right, with the same width sequence. And this means that you are basically outputting the smallest circuit. So you're not only finding the smallest size, you're actually giving a witness, a setting.
Chandan, once again, we've lost your voice.
Also, along with it. You can, in between M1 and M2, you can multiply M1 with A and M2 with A inverse, and you still, the width does not change, right? And you still get an ROVP computing the same polynomial, a different ROVP, where M has become, let's say, M prime, and M2 has become M2 prime, and so on, right? So minimal ROVPs are not unique. So the algorithm will output some minimal ROVP, and we will see from the reconstruction algorithm that essentially this is the only way you can, like a left-right multiplication with invertible matrices, is the only way you can generate minimal ROVPs for F. At a high level, the algorithm has two steps. At first, it will discover the width sequence. And I think this is the part which I think Ramprasad might have covered, and this will give you the smallest size. And after it discovers the width sequence, it will construct N1, N2, N3 sequentially, starting from N1. Right? So step 2 is the real learning part. Okay, so how do you do step 1? So here is your product, M1 through Mi, and Mi plus 1 to Mn. Just divide it somewhere in between, say at the ith position, right? And call that width there, which is basically the number of columns of Mi and the number of rows of Mi plus 1, that's Wi. Call that W, yeah, for the convenience of notation. And Xi be the variables from Xi to Xi. That's bold xi, right? This set, and bold yi be the remaining variables. The product of the first I many m's, that's a row vector, right? Because the first one is a row vector, and the product of the last remaining mi's, that's a column vector. So this row vector I denote by g1 through gw, and the column vector I denote by h1 through hw. So now notice one thing: f is basically an inner product of this g vector and the h vector, right? So it's gi, hi, but they are in disjoint sets of vectors. Fine. Let's begin with a very, very useful observation, and that's the fact that GIs and the HIs, they are linearly independent. Why is that? Why should the GIs be linearly independent? Because if not, then there exists an invertible A such that if you multiply A to this row vector G1 through GW, it becomes shorter, right? Some of the coordinates become 0, right? And if that happens, then you can multiply A inverse with H, right? And the H vector, and it will still compute the same polynomial if you take the inner product of these two, right? And now you see that these last coordinates are 0, so you can as well throw away those H's and reduce the width. So what it means is that W is no longer the minimum width. You can decrease WI further. Right? If you do that, then it will violate the minimality assumption, which is the sum of the widths, right? The size is the sum of the width. So that's why and the same thing, same kind of argument holds for the HIs also. So that means in any minimal ROVPs, no matter where you are splitting, the corresponding G vector and the H vectors will consist of polynomials that are linearly independent. Fine. So now I give you the algorithm to do step 1. What you do is you pick random points, B1 through BT. These random points are meant to substitute the Y variables. So once you pick B1 through BT, substitute the Y variables and form Fxi B1 to Fxi BT, starting from F. F is with you, right? You have black box access to F. The claim is that if you choose large enough T, especially like in particular, if T is larger than W, then the dimension of the space spanned by these T polynomials is exactly W. This will give you exactly the width Wi with high probability. Why is that? That is because of a very easy to verify fact and using Schwarz-Zippel lemma. And it's a very simple but cute thing that gets used a lot in reconstruction algorithms, that if you have a bunch of polynomials, f1 through ft, multivariate polynomials, and suppose they're linearly independent, and if you pick random points a1 through at, the same t, right? Yeah, these points are meant to substitute the x variable, and then if you form this square matrix where the f's are evaluated at a's, it's a t by t matrix, then the rank of this matrix would be t with high probability. Right, so this is an application of the Schwarz-Zippel lemma. Basically, that basically show that if you pretend the a's are variables, then as a formal polynomial, the determinant is non-zero, and hence it would remain non-zero if you pick a's randomly. Right. So let's use this fact to prove claim 1. By the way, I should make one point here. Claim 1 is just saying that the dimension of the space spanned by these elements is W. I can get access to these individual elements, but I still have to tell you how do I compute the dimension of the space spanned by this, right? So that I'll tell you a little later. Let's first look at the proof of this claim, which is fairly simple once we have fact star. That's because of just imagine an evaluation of fxi where the y variables are replaced by bj. It's just the h polynomials are evaluated here, so it looks like this, right? So if you write it as as a row vector times a matrix, you get this entire row vector is equal to this row vector g times a matrix h, which is coming from the evaluation of this h polynomials at the bij's. In particular, h is this matrix, the evaluation of h at different b. it need not be a square matrix, because it becomes a square matrix when T is W, right? But T can be greater than W. So I'm making this claim for any T larger than W, right? So, and with high probability, because of fact star, because the HIs are independent, right? So linearly independent, that was the first observation, observation 1. Because of that and fact star, I can now say that the matrix has full rank, has rank W. And because it has rank W, I now see, and the Gs are also F linearly independent, right? So G1 through GW are F linearly independent. H has rank W. So if you multiply this with H, you can only get a bunch of polynomials that have rank W, right? Or the space spanned by them has rank W. Right? So that finishes the proof of this claim. But we are still not done with step 1. Just one more thing, because this gives a clue, right? That I can find the minimum width if I can find the dimension of this space, right? So I have to now tell you how to find the dimension. I have access to the elements that span the space, but how to find the dimension. In the algorithm, what you will do is you will start with T equals 1, then you go to T equals 2 and 3 and so on, and you keep increasing T, right? And at some point you will see that your dimension is no longer increasing. At that point you will stop, right? So right, so how do I find the dimension? That's because of another claim. Let me call it claim 0, right? And the proof of claim 0 is also using fact star and observation 1, and that's the following: that given black box access to F, sorry, I lost connection again.
Yeah.
No,
The
no,
screen share
certainly
stopped.
you're not. Yeah.
Yeah.
I mean, he seems to get it
Okay.
before us. So, yeah, let me just check. Yeah, no, now you're visible.
Yes, now claim 0.
Okay.
We have the slide with claim
Okay.
0 on it.
Right. Okay, good. Right. So yeah, thanks. So what claim 0 says is that if you have black box access to F1 through Ft, then you can compute black box access to a basis of the space spanned by F1 through Ft in randomized polynomial time. It's not too hard to imagine this after you see fact star. If you just think for a couple of minutes, you'll see the proof of claim 0. And this is what you use. You get black box access to these individual elements, and then you use claim 0 to get a basis of it. Actually, I don't need a basis. Like just getting the dimension is good enough, but you can do more. You can actually find a basis of it in polynomial time. And this finishes step 1, right? Which will discover Wi, for all I, right? And from there you get the width sequence, and you also get the minimal sized ROEB. Right? The moral of the story is it just hinges on one my main observation. That's observation 1, that in a minimal size ROEP, that the row vector that you are getting at the left and the column vector that you're getting at the right, they are F linearly independent, and that is what is helping you to find what your W is.
Yeah.
Now, this dimension is something fundamental, right? So let me say what it is usually called in the literature. It's called the evaluation dimension with respect to the Y variables of F. Right? It is defined as the dimension of the space spanned by f x I b, right? Where b is any point. Right? You are evaluating the y variables at all possible points and taking the span, and that is your evaluation dimension of f with respect to the y variables. Now, what claim 1 basically says, stated differently, is that the evaluation dimension of f with respect to y is exactly w, right? And that it can be computed. Right? So it also says, if you include claim 0 along with claim 1, it says the evaluation dimension of f can be computed efficiently. If you think for a moment, you'll see that this evaluation dimension is nothing but the dimension of the space spanned by a bunch of partial derivatives, not all of them, especially the partial derivatives with respect to the y variables. right? So all possible partial derivatives with respect to the y variables. And that dimension is easy to compute for any f. That's the summary of step 1.
Okay.
Right? So yeah, sorry.
No. Yeah, no. Yeah, that's a good way of remembering it, actually. Yeah.
Yeah. So, but I should mention one thing that this is quite nice. Because if you wish to now compute the dimension of the space spanned by all partial derivatives, that is a hard problem, right? I mean, it's not to be a hard problem. A few years before Pascal Coiran, along with others, and sorry, I'm forgetting the names of the other authors. They showed like computing the dimensions of the space spanned by all partial derivatives, that is hard. But if you look at just these partial derivatives, then the space spanned by them is easy to compute, the dimension of the space spanned by them. Okay, so now let's do the more interesting part, the learning part, which is step 2. Now that I know the width sequence, how do I construct the matrices M1, M2, M3 one by one? That's because of another claim, which is claim 2, which I'm going to use repeatedly in this learning process. It says that not only you can find the evaluation dimension, you can actually find this decomposition. You can actually write F as some products of G1 prime, H1 prime, right? W of them, right? Where Gi is dependent on only the X variables and Y is dependent on the Y variables. And you can find black box access to these Gi primes and Hi primes, right? And that's, I'm going to show you a quick proof of it. How is this done? And at the heart of this step 2, this is claim 2 is what is helping, that you can actually find a decomposition of F, right? A witness of the fact that evaluation dimension is indeed W, right? The Gi stars, the Gi primes and the Hi primes again would be F linearly independent. Okay, so quick proof. First, how are Gi's found or Gjs? You do the following: you pick W random points. W as before is Wi. So I'm just removing another subscript. So you pick W random points and substitute in place of the Y variables. And the jth substitution, you call it your Gj prime. Yeah, call it. Why does it work? That works because of the following. Right? We have just seen that this relationship, right? A few slides before that, the evaluation vector, right, of F relates to the G vector like this. It's the G vector times H, right? So we have seen this a few slides back. Let me take you to the slide here, right? So it is just this, right? This equation is what I'm writing again. The H vector is the evaluation of this H, right? So full rank matrix. Why? Because you've chosen the B's randomly. And this we just saw a few slides back. So now I'm suggesting that you call this your left hand side here. That's your. If F is G times H, then I can insert some invertible matrix H inverse, and that will give me still a bunch of polynomials that are F linearly independent and a bunch of H polynomials again that are linearly independent. And that's still a valid decomposition of F. So I can't hope to recover the G's and the H's uniquely, because uniqueness doesn't hold here. So it makes sense, right? So now that the G is defined like G prime is defined like this, I can as well take this as my G prime. Now it turns out once G prime is fixed,
Chandan, you're muted again.
H prime is unique, right? So a crucial. Sorry, can you hear me now?
Yeah, now we can hear you.
Yeah, we lost you for about 5 seconds, but now it's back.
Yeah.
Yeah, so I think my connection is a bit choppy here. Right. So correct. So right. So the point here is you define G prime like this, just the evaluations of F, and then H prime gets uniquely defined, right? Why is that? That from black box access to this, let me try to recover the H primes, right? And we'll see in the next two lines that it gets uniquely defined. You pick A1 through AW randomly, right? And these A's are now meant to substitute the X variables, right? And you substitute the X variables with the A's. This is now a column vector. And now in the same spirit, you will get a matrix G, where G is the evaluation of the G primes, that's the W by W matrix, times this column vector defined by the H primes. And again, with high probability, because the G primes are linearly independent, this is a full rank matrix. You can multiply the full rank matrix to the left, and that will give you your H prime. And it would be unique, right? Because yeah, so
correct.
Yeah, so that's the point. The once G prime is fixed, H prime gets defined uniquely, right? So anyway, so let me just summarize again by saying, like, coming back to claim 2, that you can find a decomposition. The decomposition is not unique, but two things I will take forward from here. Whatever G prime I find, that G prime is related to the original G via a matrix H, an invertible matrix H. And the second thing is, once I fix G prime, H prime is also fixed, right? You can find it like this, uniquely like this. Okay, so in the rest of the argument, because I'm going to tell you how to recover N1, then N2, and so on, I will assume that all the bits are the same. They're W, right? So okay, it seems I'm running out of time. How much time do I have, Vivi?
Well, actually, it is just getting over, but how much more do you have to present?
Yeah, I have quite a bit. So anyway, it doesn't matter. Maybe I can just conclude this and in another 5-7 minutes. And
Yeah,
I'll take, and then take another 2-3 minutes to show the last part. Maybe altogether another 10 minutes or 12 minutes.
Sure, I think it's fine. I don't know about the others. Yeah, I think it's okay. Yeah, go ahead. Whoever.
All right. So now we construct the matrices sequentially, right? So let's say I want to construct N1. N1 is a row vector, right? It's this row vector G1 through GW, right? And it's not uniquely defined. So instead of G1 through GW, I can as well choose my N1 to be G1 prime to GW prime. How will it relate to the original M1? As I just said, that the G prime and the G's are related by this an invertible matrix H. So N1 and M1 will relate like this, where H is an invertible matrix, right? I'm writing in green. So in the following slides, whenever I write in green, it means that the algorithm now knows these polynomials, right? So N1 is known. Okay, so now what do I do? Once the G's are known, the H's are also known, the H primes. What is my H prime here? It is unique, so it's the remaining part. It's H inverse M2 to Mn. I don't know the individual M2 to Mn, but I know that their product is this column vector H prime, right? which is what I know. You multiply the H inverse with M2, you get M prime, right? And our next task would be to recover M2 prime, right? But M2 prime is not unique again, because you can do left-right multiplication. You can multiply something to the right of M2 prime and make it a different matrix. It's not uniquely defined. To create some kind of uniqueness, I'll define a canonical form for M2 prime, right? I'll do it only for M2 prime. And once we see how to recover M2 prime, the rest of the algorithm would be very similar to recover M3 and M4 and so on. So here is a canonical form. The claim is that without loss of generality, I can assume that M2 prime looks like a matrix whose first rows consists of matrices P11, polynomials P11 to P1S1, right? And they're linearly independent. Why can I do this? Because if they're linearly dependent, the first rows I can always multiply M2 prime by a matrix A to the right and assume that the first row here consists of only linearly independent polynomials. Once I do this, I move on to the second row, and I can't do much with these here. The deep reds polynomials mean they're linearly independent, right? So then I can ensure that the next chunk P2S1 plus 1 to P2S2, they are linearly independent. Again, by multiplying M2 prime to the right by another invertible matrix. Right, so I can keep doing this. They are not unique, right? Because I can always multiply invertible matrices and sort of garble up the PIs, right? They're not unique. And these for example, P21 to P2S1 that you see, even they are not unique. Why? Because you can always add, yeah, or take any linear combinations of the red P's here and add it up with a P here. You can do this because without actually touching these P's, because of the zeros here on top, right? So there is non-uniqueness of the P's here, and the P's even at the bottom there's non-uniqueness. But we'll remember these two things, and this will help us recover N2. Right. So let's see how we do this. Let me just do it for the first row and the second row. Right? They look like this, right? And let me call this remaining part M3 to Mn, right? With this A inverse multiply. The A inverse is coming from A because I'm assuming canonical form, and that takes an A, right? So that's why this A inverse. Let me call this column vector Q1 through QW. By the very definition of minimal ROP, we now know that Q1 through QW are F linearly independent, right? And this will help us. Okay. Another thing we know is the H vector from the learning of N1, right? The H1 prime vector looks like the product of M2 prime A times Q1 through QW, right? So that's from the very definition of the Q vector. Okay, now let's look at just the first coordinate of H. How will it look? M2 prime A is in this canonical form, and that's multiplied with this column vector. So if you expand, if you just take the first row and multiply it with this Q vector, you get this. That's your H1 prime. In green, so I know H1 prime, right? And they are all linearly independent. So I can apply claim 2 and know a decomposition. Right? It won't be unique. I won't be knowing the actual P11 to P1S1, but I will know some P11 prime to P1S1 prime. And I know they are related nicely via an invertible transformation. Right? So what this means is that the A, I can as well assume that this was not my A, this was some A prime. And instead assume that my first row is actually P11 prime to P1S1 prime. Right? And similarly, my Q's, part of it is now known. Which part? The Q1 prime to QS1 prime. That part is known now, right? So at the cost of that A has now become A prime, but it doesn't matter. The algorithm doesn't care about A. It just wants to find some N2, right? Okay, good. So now after this, I know the first row. How do I find the second row? Okay, the second row. For the second row, you look at the same equation here. And look at the second coordinate. H2 prime, if you expand, it's the second row times the column vector Q prime. And if you expand it, you get this P21 prime to P2S prime times this known Q part, which is already known from the step before, plus this red P2 part times the a part of the Q prime. Okay. So how does it help? A lot of things are not known, but part of it, the green parts are known, right? Now you again choose random points, B1 through BS1, and you plug in place of the Y variables, right? And wherever they have Y variables, you plug in Y2 variables, right? So Y1 is X2 plus Y2, right? You plug in place of the Y2 variable. So this Q prime now gives rise to an invertible matrix Q, which is known to you, and because you know the Q prime. So if you multiply Q prime to the right of H prime, which is known, you get your P prime plus this. Now you see the P prime, the P2 primes here, they are not unique. They are unique up to linear combinations of the red the deep red P2s, right? And that's what we are getting here. So why not take the left-hand side as my P2 primes, right? So I take that as my P2 primes, and henceforth, I can now assume that this part is known, right? So because it's not unique, so I can do the best I can do is learn them up to this linear combination. So I learned them. So this is known, yeah. So I can now. So I'm sort of abusing notation. I'm no longer changing A prime to A double prime now. I can sort of pretend that okay, it's the same A prime, and now this part is known. Now, if you look at the same equation now, this whole P2 prime is known, and you just take the first term to the left, and you get an equation like this. Right? This is pretty much like what is needed to apply claim 2 again. Right? If you apply claim 2 again, you get this decomposition. Right? You decompose and get the deep red P2s. Right? So and that's how you learn the deep red. Right, via another decomposition. Again, it is not unique. The best you can do is to learn something which is spanned by the deep red P2s. So you learn them, and your A changes to A double prime, and you keep doing this, right? And that's how you discover N2s. All right, so this is how you do it. It's a sketch of it. Sorry, I rushed a little bit. Let's do, that's the end of RAVP reconstruction. And people have also studied Reed-One's formula reconstructions, and there are known randomized polytime algorithms. There are known deterministic polytime algorithms also, and it is a proper learning. So Reed-One's formula is strictly contained in Reed-One's RAVPs, and I won't be going into that. It's just for the purpose of mentioning. What I'll go into, and maybe if I can allow me another 2 minutes, I'll just quickly show. The last bit is, let's come back to Waring rank, right? So we did improper learning, but let's ask again, what about proper learning? Like, I know it is hard, but what exactly can we do? Like, can we, for example, do proper learning of powering circuits when the rank or when the top fan-in is a constant? It turns out that we can. We can do this if the Waring rank is a constant. Then we can actually learn it in polynomial time, right? So lots of people have studied depth 3 reconstruction with constant of fan-in, general depth 3 reconstruction, right? So here is a brief summary of the known results. So let me not read it out, but let me quickly show, because it's a very short and cute idea. How do you learn depth 3 powering circuit with constant Waring rank? And let me just flash it in 2-3 slides. The idea is the following. Let's say you have a depth 3 powering circuit. Now I want to do proper learning. I want to actually find the linear forms. You have black box access to F. You want to get a circuit, a powering circuit. The algorithm has 2 main steps. First, you remove the redundant variables. And second, you solve a system of polynomial equations in k-square variables. What is k? K is the top fan-in. It's a constant now, right? Okay, so what does it mean? Right, redundant variables and so on. So let me just quickly define what redundant variables mean and essential variables mean. The essential variables, it's the number of essential variables. It's the smallest k such that f(a)x, right, depends on only k variables, where A is an invertible matrix. Right? So you can think of like this, like you keep applying invertible transformation to F. Whatever is the smallest number of variables you come up with as you keep applying invertible transformation, that number is the number of essential variables of F, and the remaining numbers are redundant. Right? It makes sense to call them essential variables because applying invertible transformation is, geometrically speaking, is like rotating the function or reflecting it, or doing things. It's just rigid transformation, right? So it's basically saying you can choose a coordinate system where F depends on only k variables. So that's why we call k the essential variable. It turns out that you can actually find the essential variables, and you can actually find a transformation A that will reduce the number of variables and keep only the essential variables. It's an algorithm due to Carlini, and Kayal built on it and gave a randomized polytime algorithm. And that's because of a very nice connection, a very exact connection between the number of essential variables and the dimension of the first order partials of F. So just let's take this forward, that I can actually reduce the number of variables and keep only the essential variables. And now we are done. Right? So I think that this is the last slide, actually. So you know one thing, that if there are k
Chandan, 1 second, we've lost you. You're muted.
linear forms, the dimension of the yeah, can you hear me now?
Yeah. So you were reading the first sentence when we lost you.
Yeah. So I was just saying that because the dimension of the space spanned by the first order partials of F is at most k, that's because every partial of F is a linear combination of L1 power something, right? D minus 1, some linear combination, k many of. So the dimension of the first order partials of F is at most k. And that means that the number of essential variables of F is also at most k. And there is an algorithm to compute A such that if you apply A to F, these linear forms will now become LIAX, right? But I know that this will depend on only k variables, the first k variables, x1 to xk. So you can set the remaining variables to 0, and your g1 through gk depends on only k variables. So you have k many g1 through gk, each depending on at most k variables, right? And that's the crux. And this is the main observation, and the rest of the thing is like brute force. So what do I want? I know A, right? I want to find my G1 through GK. So you pretend that your coefficients of G1 through GK are variables. How many unknowns are there? K square many. K many G's, each having K many variables. And you learn the depth 2 representation of Fx completely. You learn the dense representation of Fx, right? And now you equate the left-hand side, the coefficients of the monomials of the left-hand side with the right-hand side. The right-hand side, the coefficients of the monomials would be polynomials in the unknown coefficients of G1 to GK. And left-hand side, the coefficients would be known because of sparse polynomial interpolation. And you equate them and find the unknowns G1 to GK, right? And this can be done because there are efficient algorithms to solve polynomial systems. Sorry, this is the last technical side. Right, I'm sorry about it. And you apply polynomial solvability, which can be done in randomized polynomial time if your number of variables is a constant. Can be done over complex number, real numbers, finite field, right? And that's what this algorithm exploits, to learn all the G's, and that's it. So you can do proper learning. Of depth 3 powering circuits in polynomial time, if the Waring length is constant. So that's it. Just to summarize, we discussed worst case reconstruction, went into the details of ROEP reconstruction and proper learning of Waring decomposition of powering circuits for constant fan-in and sparse polynomial interpolation. That's it. In the next talk, I'm going to talk about average case reconstructions, by centering around the same model, which is depth 3 powering circuit. Yeah, thank you so much for your patience and giving me extra time.